Hello and welcome back to Josh Does Math. In this video we're going to be looking at the differentiability of a function. So that's the ability to take a function's derivative. And we have four functions right here. We're going to figure out which ones are differentiable and where they're differentiable and where they're not differentiable. So looking at the first one here, the root of absolute value of x. So first of all, what does the root of x look like? So that looks like this. So now if I'm taking the root of something, I'm always taking the root of something positive. So by putting absolute value under here, that's not really doing anything for all of these x values that are positive. However, by putting the absolute value in here, I can now put a negative number into this function, and it will give me whatever is over here. So how the function used to work with just the regular root of x is if I put in, let's say, 4 for x, it would give me 2. Well, now that I have absolute value in there, let's say I put in negative 4. It's still going to think I'm putting 4 into it, and it's going to give me 2. So for all negative numbers, you're just going to get a flipped version of it like that. So where is this differentiable? Well, it's differentiable if it's, in order to be differentiable, the function has to be continuous and the left-hand limit of the derivative has to equal the right-hand limit of the derivative. So on a graph, this just looks like a smooth graph. You don't want any sharp points. Well, this looks like a pretty sharp point right here. So we'll say that this is not differentiable at x equals 0. How about the next graph over here? Absolute value of x squared minus 4. Well, what's x squared minus 4 going to look like? We know that x squared looks like this. So x squared minus 4 is just going to be me shifting this parabola down by 4 units. So I'm just going to shift the parabola down. So that's what it's going to look like. And now we're taking the absolute value of this entire equation. So what does that do? It just makes everything positive. So what is the absolute value doing right here? Absolutely nothing. What is the absolute value doing right here? Absolutely nothing. What is it doing down here? It's going to flip that up and make it positive like that. So I'll redraw this function down here. It's going to look like that. See how it just flips it above the x-axis there? So where is this function not differentiable? Well, it's not going to be differentiable at the sharp points, which are right here and right here. And those are the values where this function is equal to 0. And it's the values where the original that we made up here, just x squared minus 4, was equal to 0. So we can solve a simpler equation instead of messing with the absolute value. We can just look at where this was equal to 0. So I'm going to solve this for x, and I get x squared is equal to 4, so x is equal to plus or minus 2. So at x is equal to plus or minus 2, this equation is not differentiable because of the sharp points. How about this equation over here? Let's graph that. First, I'm just going to graph 2x minus 3. So 2x is going to be a steep slope minus 3. That's going to shift it down, so it's going to look like this. Now, if I apply the absolute value, just like in this example over here, it makes the whole line positive. So we end up actually having this line up here that does not change at all. And then this gets flipped up and becomes the positive version of what it was. So it's now going to end up having a slope of, I guess, -2. So this is our new graph right here. You can ignore this down here. That's what this graph is. Well, where's this one not differentiable? It's going to be at this really sharp point right there. Well, what is that point? It's going to be where the line crosses the x-axis. And we can use the original equation, 2x minus 3, instead of messing with the absolute value because it crosses at that same point right there. So say 2x minus 3 is equal to 0, and we're going to solve for x, and that will be the x value where this sharp point of non-differentiability is. So 2x is equal to 3, which means x is equal to 3 over 2. So at x is equal to 3 over 2, the function is not differentiable because of that sharp point right there. How about this function? X times the absolute value of x. So we'll use the same tactic we used for these other problems, and we'll take the absolute value out and then try to add it in and see if we can modify the graph that we had. So imagine if we take the absolute value out. This just becomes the graph of x squared. And we know what that looks like. So that's what it looks like with the absolute value out. Now imagine if we were to apply the absolute value to just one of the x's. How about we'll look at whenever x is positive. When x is positive, this absolute value is doing absolutely nothing. So this part of the graph over here, this part that's in the positive area, that remains the same. What about for the negative x's? If I'm applying absolute value to one of the negative x's, making it positive, but the other x remains negative, a negative times a positive, it's going to give us the same magnitude of value, but now it's going to be negative overall. Because as it used to be, we would do a negative times a negative, that gives us a positive. Okay, and we're fine. The whole graph is positive and it's that parabola shape. But now, since one of our negatives is not being canceled with the other due to the absolute value, our graph is instead going to look like this. This part remains the same. The other part is now negative. It's going to look very similar to if I were to draw x to the third. So it's still a parabola shape, but that instead curves down for half of it. So it doesn't suddenly turn into x to the third, but it just mimics that shape. So this is what the graph is going to look like. So where is this not differentiable? Well, it's differentiable everywhere, right? It looks like a pretty smooth curve right here. There's no points where it's sharp. So we'll say points where it's just not differentiable. Say none, because there are no x values that make a sharp point for that graph. So that's how you can look at functions that are graphed and just figure out where they're not differentiable without doing too many limits and complicated math like that. We're just looking at graphs and looking for points where it's sharp, and that's going to be a point where it's not differentiable. Thanks for watching.